In 2004, a great film called The Butterfly Effect was released. I'm sure many of you have seen it. It's about a man who suddenly gains the ability to travel back in time simply by reading his old diary. This allows him to remember past events he had forgotten. Miraculously, any changes he makes in the past affect his future. He uses this power to prevent bad things from happening to him and his friends.
I mean, let me get the hell back!
But what happens is, even though he succeeds in preventing one terrible event, it only leads to a worse future. He's then forced to go back in time again to change things. But the same thing keeps happening. One bad thing is fixed, but another unexpected one always appears. The film has an interesting message. Even if you could travel to the past and change it, you still couldn't know the future. This is because the smallest change you make will trigger a series of major events that you cannot possibly predict.
Play God, son.
This isn't just a message from a movie, as the film was inspired by a famous mathematical phenomenon also called the butterfly effect. The butterfly effect is the idea that there is no single formula that can predict nature with complete accuracy. Any forecast or prediction, even one made with a computer, will be thrown into chaos by a tiny error that is impossible to detect. It's said that a weather forecast can be thrown into chaos by a single flap of a butterfly's wings.
The natural world could be deeply, profoundly unpredictable.
It would be very hard to predict, for example, with a computer.
You can have the simplest equations you can think of. Then you can never know the starting point accurately enough.
We don't know anything perfectly in nature.
At the beginning of the butterfly effect, a quote is shown as, "It has been said that something as small as the flutter of a butterfly's wing can ultimately cause a typhoon halfway around the world." Chaos theory. We'll talk about what that means later, but first, you have to understand chaos theory. The word chaos comes from Greek and means emptiness or disorder. According to Greek mythology, the universe began from chaos. From chaos came the gods, such as Gaia, goddess of the earth, Eros, god of love, Erebus, god of darkness, and so on. Their children and grandchildren included Zeus, Hera, and Athena. We won't discuss these gods, but the point is that people once believed everything that happened in the world, rain, lightning, typhoons, and storms, was the work of the gods.
However, during the Hellenistic era, as Greek myths began to separate from rational thought, philosophers started looking for more logical explanations. They felt that nature wasn't as mysterious as people imagined because it seemed to have a pattern. They called the universe a cosmos, the opposite of chaos, meaning an orderly world. This led to people like Copernicus, Galileo, and Kepler trying to formulate how the universe worked. The peak of this was in the 17th century when Newton published Philosophiae Naturalis. In it, he precisely formulated how celestial bodies and objects around us move, which we now know as Newton's laws of gravity and motion. Through these two laws, Newton seemed to give us a very accurate calculator that allowed us to predict the movement of objects from the smallest to the largest. Clockmakers at the time even built replicas of the solar system, driven by a machine called an orrery.
This instrument is called the grand orrery. It epitomizes the ingenuity of clockmakers to show the motions of the planets so that you could predict where the planets would be at any one time. And so it had a wide usage in showing how the universe was really a giant clockwork mechanism.
Newton believed that the universe was like this machine where all of its movements were patterned, making everything in the world theoretically knowable. This was the golden age of science, where it developed tremendously and overcame all the myths. In the 18th century, the French mathematician Pierre-Simon Laplace said, "If we could measure the exact position and motion of every particle in the universe, we could know the future just as we know the past." When Napoleon Bonaparte asked him about God, Laplace replied that God's role was not needed in the regularity of the universe. Unfortunately, the beliefs of Newton and Laplace were disproven a century later by the findings of another French mathematician named Henri Poincaré. He said that it was impossible to accurately predict the universe because he discovered chaos.
Solution to the three-body problem. With three suns in the sky, every civilization ends in chaos.
Because if it keeps tugging on it, it keeps pulling it away. And the previously stable orbit would just decay into chaos.
The three-body problem was a real issue Newton faced when formulating gravity. Newton had only formulated gravity for two celestial bodies, but when he included a third body in his calculations, the results were chaotic. Newton wondered, with so many elements in the sky, why was it stable? He eventually gave up and said the universe was stable not just because of mathematical calculations, but because God had a role in keeping the stars and planets in their orbits.
Well, Newton believed in the stability of the model, but he still had his deepest questions, I guess, about the connection between the model and the real solar system. So he believed that the solar system, which obviously had several more planets, but also comets and other strange phenomena, that there, in order to keep it on a regular track, that it was necessary for God to push with his divine finger the reset button of the universe annually and keep things going the way they were supposed to go.
The most interesting thing is that Newton's frustration led scientists to a new and astonishing discovery. Nature has a unique pattern that makes it impossible to predict entirely. This is called chaos. But here, you have to note that chaos doesn't mean random or disordered. It's something with such a high degree of order that it becomes impossible to predict. To understand this, look at the animation. You can see two balls. One looks regular, the other looks chaotic. That's because the regular ball is attached to a single pendulum. But wait until you see this. The chaotic ball is also attached to a pendulum, but it has two arms. You can even try this at home if you have a pendulum like this. The point is, no matter how you swing this pendulum, its motion will eventually become chaotic.
You'll see the sort of very irregular, hopefully you'll see the very irregular kind of way in which the lower pendulum oscillates around. And it would be very hard to predict, for example, with a computer, how that lower pendulum, will it go around once more? Yes, just made it.
What's unique is this. If you shift the starting position even slightly, for example, here we see simulations with slightly different starting positions. The tiny difference will result in a completely different trajectory. The balls end up on different paths and look random. Another example is this magnet pendulum with other magnets placed below it. No matter how many times you try to swing it from the same position, it will never follow the exact same path twice. This is because you can never and will never be able to place the pendulum in the exact same spot as before.
When the magnet approaches the fixed magnet, it can go either to the left or to the right. Which way it goes depends very sensitively on exactly where it is when I release it. Similarly, at any other point along its trajectory, which way it goes will depend on exactly where it happens to be at any particular moment.
This phenomenon is called sensitive dependence on initial conditions. It means that the smallest change in position, even a tiny fraction of a millimeter, will change the entire trajectory. This is a characteristic of chaos. And it's what Henri Poincaré discovered. Nature is not as simple as Newton thought. Unfortunately, almost everything that happens in this world, and perhaps everything, has chaotic characteristics like this pendulum. One of the most fitting examples is the weather. Weather is one of the things humans most want to predict. We want to know if it will rain today and whether it will be a drizzle or a downpour. Humans have tried to forecast rain for ages, whether using a shaman or technology. Unfortunately, even technology often doesn't help because the weather itself is the perfect example of how chaos works. In the 1980s, scientists, more specifically meteorologists, tried to forecast the weather for the first time using a computer, as computers were rapidly developing. One of the pioneers of computer-based weather forecasting was Edward Lorenz. He created a program to simulate weather using 12 weather parameters like temperature, air pressure, humidity, and so on. He thought that with these 12 parameters, he could forecast the weather for 2 months ahead. One day, he started his first simulation. After it was finished, he tried a second simulation to verify it, but this time, he didn't start from the beginning. He started from the middle, inputting a value he had obtained from the previous simulation. He went for a coffee break and was surprised when he came back to find that the graph was diverging. He initially blamed his computer for an error, but it wasn't the computer that was wrong. It was because of one small mistake. He input the number with a precision of 3 decimal places, while the computer calculated with a precision of 6 decimal places. If you have some mathematical sense, the difference between 6 and 3 decimal places is very small and should have been negligible. But with this small difference, the graph Lorenz got diverged significantly.
And I was rather dismayed at first when I came back an hour later after 2 months of simulated weather and found that it wasn't behaving the same way because we'd had a lot of trouble with our little computer, and I thought this was more computer trouble at first. And then when I looked at it more closely, I realized that what was happening was that I hadn't put the same numbers in. I'd put in rounded off versions of the numbers, and these small differences had amplified, doubling every few days until they became so large that they drowned out the signal.
Remember, the graph represented the weather, determining whether it would be sunny or raining heavily. If the graph diverged so much because of the trivial thing, it meant that nature was fundamentally unpredictable.
When I was a graduate student, the belief was, as we got more and more computer power, we'd be able to solve ever more complicated sets of equations. But this said that's not necessarily true. You could have the simplest equations you can think of, with nothing random in them. You know everything. If they have behavior that gives you chaotic solutions, then you can never know the starting point accurately enough.
This situation led Edward Lorenz to write an article titled, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" Of course, Lorenz used the butterfly as a metaphor. The point is that weather forecasting can be disturbed by something as small as the flap of a butterfly's wings. Because of Lorenz's article, the term butterfly effect became very popular, used not only in physics and mathematics, but also for any phenomenon where a small disturbance leads to a chaotic situation. Yes, including in movies. Getting back to Edward Lorenz's discovery, 2 researchers from MIT tried to figure out what was really happening with his formula. They created a graph using an analog circuit, which was later called the Lorenz Attractor, and this is the image that appeared. The image itself looks like butterfly wings. So what does this image mean? Notice that each point on this trajectory represents the weather being forecasted. The surprising thing is that the point continuously takes a different path and never intersects with the previous path. If you rotate the image, because it's three-dimensional, you will clearly see that they do not intersect at all. Many of you may still be confused by this image, but the point is that it shows that no matter how hard you try to predict something, nature seems to continuously evade you by taking a different path. This is why you can never be 100% accurate in your predictions.
What Lorenz's work tells us is that no matter how complex our models become, and no matter how good the initial data becomes, there will be a limit beyond which we cannot provide accurate forecasts of the instantaneous weather.
What Edward Lorenz and Henry Poincaré discovered became a new field of study called chaos theory. The more they studied it, the more they found that almost all random phenomena in the world, like water currents, mountain formations, tree branches, and even the human heartbeat, have chaotic characteristics. Again, chaos in this context doesn't mean disorder, but rather a pattern that is so highly ordered that it's difficult to predict.
They discovered that the natural world could be deeply, profoundly unpredictable. But the very same things that make it unpredictable also allow it to create pattern and structure. Order and chaos. Seems the two are more deeply linked than we could have ever imagined.
But here you must note that even if things can't be predicted, it doesn't mean all of science is useless. The technologies you use every day are a product of science. Chaos theory simply teaches us that there are still many things that are beyond human comprehension. What we have learned so far is just a drop of water in a very vast ocean.